All right. And now it's my pleasure to introduce Professor Roozbeh Hazrat from Western Sydney University, who has been so kind to travel all the way from Australia to to tell us about Leavitt path algebras, monoid, and other.
Yeah.
Okay.
All right. Thank you so much. So is that okay, the sound? Okay. So I'm gonna talk, a big part of the lectures is about monoid, but let me just motivate what we are going to do here. So we start with some combinatorial objects. So I'm not going to define what does it mean, but you're just picking some discrete objects here, maybe just 3 points at the moment. They have nothing to do with each other. And then you can associate different algebraic structures to this. One of them is some sort of algebra. And in my head, it's really that Leavitt path algebra associated to a graph. You can do Cstar algebras. You can associate directly from here a monoid. Oh, okay. Oh, yeah, okay. So combinatorial. A combinatorial object, then an algebra you construct just directly from here. You can do a Cstar algebra. Now this one has norm and topology. You can construct directly a monoid, and this is what I'm going to concentrate here. But then you can also construct a groupoid. You have seen, for example, in the work of Gilles, he started with a groupoid. And there are other things. Let me just put here also inverse semigroup, whatever they are. Inverse semigroups. Okay. And as I said, these combinatorial objects could be just maybe 3 points. Then whatever you get, maybe in the monoid, you get n copy. With this construction, you get just 3 copies of n. This construction here, maybe you get 3 copies of your quotient field or ring. I don't know, maybe here you just get the same 3 points in the category with just identity map. So you just construct things. But this is not very interesting, but it gets more interesting if the objects here have some kind of relationships with each other. So I just realized that with just drawing some sort of arrows. Then it becomes a directed graph. And then in my head, the construction here becomes Leavitt path algebra of this graph E. This becomes the Cstar graph, Cstar algebra. This becomes a monoid now. Let's call it ME. This becomes a graph groupoid. And this becomes, I don't remember what they call it, the inverse semigroup associated to this E. Okay, and then the next natural question is that, okay, how do you connect these all together, right? So here, these objects, how they are reflected, the structure reflected here. So, and the idea is, because the way we construct this, there is a very tight relationship between the structure, say, of monoid and the structure of this algebra, the structure of this graph, Cstar algebra, and so on. Now, the interesting thing is that, let me start from here. So this is a Cstar algebra, and that means it's an algebra. It has a topology, it has a norm, right? So it has a lot of instruments you can use. This one, I'm dropping a topology. So I don't work with continuous things. It's just very discrete. You can just multiply and add things, that's all. Now here, I'm also dropping the multiplication. It's just addition. It's basically the simplest algebraic structure you can build. You just add elements, all right? But amazingly, in this setting, although you are losing structure, but you're losing the, what do you call it? But here I'm losing the topology, here I'm losing the multiplication, but you are not losing the structure. Namely, the structure of this, hopefully you can see from here. The structure of this you can see from here. Okay, so this is the idea, that I maybe start from here and go towards the monoid. Now, this was already started with, I mean, some people say, okay, why? Yeah, this is, in fact, I applied for a grant, and the guy said, oh, okay, everything is here. This is interesting. Why do you use here? This is like, you know, maybe in 2 years people would forget that. But this started already by von Neumann, John von Neumann. He was, you know, very, very sort of influential mathematician. So for C-star algebra, to construct C-star algebra with norms, well, he had this motivation from physics. You start with some physical thing, you get this structure. But he thought, yeah, maybe if I lose norm and just start with this algebraic structure, I can capture the whole information. So he already started this, and people like Kaplonsky and Jacobs and their students also try to do this. Now we are going to go one step further and look at this monoid. And they're conjectural that maybe all the structures already reflected there. So let's start from there. So I'm going to start with commutative monoid. And by the way, this monoid itself, if I concentrate here, again, this is just nothing but if you have two elements, you would be able to add them. And people arrive to this notion from, well, algebra, from topology, from geometry. So recently, I'm looking at this different literature. You have the same notion, but it's called different names because people from topology, they call it phases. In algebra, they call it ideal. Some other places, they call it saturated sets. So just because people arrive to the same notion from different, I don't know, branches of mathematics, that's why. Okay, so I'm going to concentrate in commutative monoid, but just to motivate you, I'm going to start with a puzzle. And I gave a talk here 2 years ago, in fact, in February, and I started with that puzzle. So I'm going to repeat that, and I give you two new versions of the same puzzle. But you see that the new versions are going to totally different area. So same puzzle that you can tell somebody, you know, a primary school student. But if I change a little, then it goes in very different areas. So here is the puzzle. It's called MadVet. So imagine there is a crazy doctor, and he has 3 machines, okay? This is machine number 1, machine number 2, and machine number 3. And if you plug a cat in there, this machine would give you a dog. So you can tell this puzzle to people at home. So if you plug a dog, you would get a dog, a cat, and a rabbit. And if you plug a rabbit in there, you get a dog and a cat. And the thing is that these machines can work backward. Namely, if I plug a dog, I get a cat. If I plug a dog, cat, and rabbit, all 3, I get a dog, and so on. Okay, so you can go back and forth. And here is the question. Here is the puzzle. If I give you a cat, can you combine these machines back and forth, and give me 4 cats? Okay, I'm going to leave it there for you. It's not, this one is not very difficult, but you know, you understand I can make it much more difficult, more machines, more combinations. But the thing is, here, I always plug in left-hand side 1 animal here, and I get whatever. Okay, so okay. Now, so this you can give to a primary school student. Now, if you're thinking mathematically, let me try to make a mathematical model out of this. How can I do that? So here you have a cat, and then you transfer this and you get a dog. So a cat is the same as a dog. And then if you have a dog, you can push it here and you get a dog, a cat, and a rabbit. And here, a rabbit becomes a dog and a cat. And I can put equality here because I can go backward also. So then you have dog, cat, and rabbit. It's exactly as a dog. Okay. So you have these equations. And my question was, is it possible a cat would be 4 cat? And then you would say, okay, yeah, this is an equation, but where is your universe? Where are you working? So very quickly, I just put it here. Think about this. I'm working in this monoid, that I'm getting a bunch of cats, bunch of dogs, bunch of rabbits, anything I want, like 5 cats, 5 dogs, and any pile of animals. I get the monoid associated to this, and I divide it with these relations because I know in this monoid, this is valid. So I divide it with these relations. I call it M. And now in this monoid, I'm asking if this equation is valid. So I'm getting to a monoid. Okay. So this is eventually what it would be ME, because I can associate a graph. Maybe even you can imagine how I can associate a graph to this. And these all becomes, for any E, I have a machinery to associate a monoid, and this becomes that. Okay. Now, I need to copy and paste here. Now I'm going to change this a little. I have the same thing. How can I copy it here? So I just put it ME for this one. So this is graph monoid, eventually. Now, if I change I can change this a little. So what if now these machines, when transforming the animals, it just adds some age to them, okay? So if you send a cat of age 0, then you get a cat 1 year older. So it takes time to transport these cats. And the same here. So adds 1 to the age of the animals. And when you are going back, for example, if you have a dog age 5 and a cat age 5, they have to be the same age. Then when you go back, you get a rabbit of age 4, so it decreases, right? If you do this, you can do the same kind of things, and you'll see that. And the model I get for that, it's called TE, and this is what we call a talented monoid. You have seen this, but now you're seeing this sort of modeling. And the idea is that now I have sort of evolution also involved there. So, you know, it just goes back and forth with the age. Now, let me do one more of this. Okay. So, same story, same. Now, I'm changing the puzzle a little bit. This time, look, previously, only one animal gets in there and change. Now, what if I just say it's 3 rabbits gets in there, and then you get a cat and 2 dogs? You see, it's getting a bit more complicated. And then here I say 3 cats, and then I get 2 cat and rabbit. And then next time, maybe 2 dogs, and I get a cat and a rabbit. And this time, the question is, what if I give you 3 rabbits, and I ask you to go back and forth with these, and give me 3 cats? Well, very similar ideas, but you see that the mathematical model for this would be, maybe I call it ME this time, is a weighted graph monoid. So you'll see that also. And amazingly, they go in very different directions. So studying ME, studying TE, and studying the weighted graph goes in different directions. And you'll see that if I start with TE or ME or TE, the algebras you get are very different. In fact, For this one, you get something called a weighted Leavitt path algebras, and the relations are very different than the one that you have seen before. So a little change in the game gives you very different algebras. Okay, so that's one motivation. Let me give you another puzzle, and this is a bit more serious, and I didn't know about this until 2 months ago. And it's a subject in itself, massive subject. It's called sand pile models or chip firing, and there are books and so on about that. So let me explain what that is and how that's connected to monoids and all this stuff I just said. Okay. And this time maybe we just do an exercise together, see if we can get these going. Okay, so is this still okay? Oh, good. All right. So now, the story. Well, I tell you the story after you see what is the puzzle. So imagine you have a grid here, okay, and you have 4 objects sitting here. So in the theory, they call it 4 grains of sand that you can move them, or 4 chips. Okay, so 4 chips are here. Now, so 4 of these objects are here, and look, there are 4 edges getting out, or 4 roots getting out. So you can move these objects along here. So one of them goes, so this is 4. One of them goes here, 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 and here is 0 now. It's very simple, right? So just move them here. So let me give you one more example. And then can I ask you to do one, see that you got the idea? So imagine there are 4 chips, objects here, 2 objects here, and 2 objects here. So the game is, if there are more or equal objects than these edges getting out, you can distribute. And in the theory, they call it toppling, or they call it firing, chip firing. So that's the title of the books, chip firing. Or you topple the sands. And I think the idea is you have seen these watches here, or clocks, that the sand just goes here, toppling. I think that's the idea of sand going through this. Okay. So if there are more or equal objects, then the way you can push them, it fires. So let's do this one now. So this, I know, one goes here, one here, one here, one here. So 1, 1. 3 objects here, one goes, it becomes 3 and 3. Okay. So now look what happened here. That was 2. So it was stable. You could not fire because there are 3 things going out. It fires if there are more objects or equal than the edges. So this was stable. And now it's unstable because there are 3 here, so you can fire. So let's fire that. So 1 and 1 is sitting here. 1 goes up, 1 goes back, 1 goes here. Same story here. So this becomes the distribution of these chips. All right? So can I ask you to do this exercise? Let's do this together. And once you are done, because people can do in a very different ways, and there is a theorem sitting here that guarantees everybody gets the same answer. So can I ask you to do this one? So remember, a node fires if there are more or equal objects than the roots going out of it. And all the way, you can ask what this has to do with monoids and Leavitt path algebras. Okay. So here is an exercise. And I'm not gonna write the answer, but I want you to give me the answer and I want to write it on the board. So imagine here is 0 objects, here 4, here 4, here 3, here 2, 0, 0, 0, 0. Okay, and I want to write it here in one go. So you play this game, it's guaranteed that it stabilizes. So eventually it's going to be distributed and then you cannot move them anymore. So that's called stabilized. You get to the final stage. That's going to happen. So, and the complexity is that at the moment this is stable. This does not fire because you have two objects, but there are three roots. But if you fire this, then this becomes unstable and it fires. So you have to take all these into account. So let's give ourselves 2 minutes, and can you give me the answer? I worked this out last night. Hopefully I have not made mistakes, but I put here sand pile model. Any answer? So 1 more minute, and if you don't give me answer, I just write my own, but there is no guarantee this is correct. So Alfie, did you get it? Okay, so could you give me, so from here, let's start. How many? 0, 0, 1, 0, 2, 2, 1. Okay. So wait, 2, 2, 1. Okay. Wait, this 3, it fires again. Yeah. Okay, let's go further. Then we fire this one. And then what else? 0, 1, 1, 0. So suppose we are here. Now this 3 again fires, so it becomes 0, 2, 1, 1. Let me see. Oops. I have a different answer, but so this is the idea. Anybody got different answer? Yeah, you okay? First, this is the correct as before, yeah. Okay. All right, I think my answer was this one also. Okay, now, first of all, you see it's involved, you know, you have to do some work. Now, couple of things. maybe, I don't know, maybe Alfie started with this 4 and fired, you can do that. But maybe you started with this one, right? But there is 2 theorems here that you can prove. And if I look at this, I cannot see the proof immediately. And in fact, I'll tell you the story, and the paper has only 2 theorems, and I'm just telling you both. One is that theorem. It doesn't matter which one you choose first and fire. If you fire this one or you fire this one, doesn't matter, you get the same result. So the order does not matter, okay? And that's why it's called abelian sand pile, because it doesn't matter how you approach. The theorem 2, and this is a bit more difficult to prove, is that you keep doing this as you did, eventually it stabilizes, and you always end up with the same result, okay? It doesn't matter how you fire things, you always have the same picture. So uniquely, the system uniquely stabilizes. You have to prove this. Again, it has a proof. All right, so now, so it's like a game. At the moment, it's just a game. Now, what I would do, let's start here. And what if I put 1 million? So that shows you there is something here. It's not, there is some, some non-trivial stuff happening here. So imagine I have a large grid, very, very large grid. Okay, very, very large. And I put here 1 million grains of sand, 1 million, right? So, yeah, this is good. Thank you. Thank you. Oh, yeah, right. That's right. Okay. So you have a very large grid. Let me draw again. And in the middle sits 1 million grains of sand. Well, each 4 of them fires. Again, another 4 fires. Keep firing, right? So what do you think I would get there? So here sits 1 million grains. And this is a very large grid. So 4 of them goes and sits here, here. Oops, no. 4 of them goes and sits here, 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 here. Another 4, and then this becomes 4. This topples, goes up. It spreads, right? It spreads. And can you imagine in your head what pattern I would get if I just spread the whole thing? First of all, I know it's going to stabilize, so it's going to stop. But what do you think I would get? So if you have your phone, just Google abelian sand pile model, and you would be amazed the picture you would get. And I'm just trying to do it here. So just Google abelian sand pile model and put the image, see what you get. Because what I put here is not very impressive, but what you would see, it's very impressive. You get some sort of fractal-like picture. Very impressive, very impressive. And the way you do it, look, in each node, either sits 0, 1, 2, or 3 grains of sand, right? If there are 4, it's going to fire. So either in here sits 0, 1, 2, or 3. So I'm just assigning a color. So if the 0, I put maybe black, I don't know. 1, I put red. If there are 2 grains of sand, I assign green, and so on, maybe pink. And then, well, I assign colors to these nodes. And when you see an amazing fractal out of this distribution. And this theory has been around for 25, 30 years, and still in the literature says, we don't know why you get a fractal out of distribution of this? Is there a theory that describes that why you get a fractal? Okay. Now, let me change this to something different. And before that, now, let me tell you about the history of this abelian sandpile model. So a paper came in 1987 by somebody called Back, Tong, and Wiesenfeld. And I studied in Germany, and my supervisors was Tony Back, but this is a different Back from Denmark. And funny enough, my supervisor had a postdoc called Tong, but these are different people. So they are from Denmark. So they came up with this abelian sandpile model with these two theorems that they distribute. And then Back worked in an institute in Copenhagen, and he was very enthusiastic about this. And he wrote a book, I think in the 90s. You can also find it. It's called, the book is called How Nature Works. Ooh, okay. Not much math in there, it's philosophical. And he says that a lot of things you see in the nature has this property, has this behavior. For example, and amazingly in many different settings. For example, and we have this problem in Australia, bushfire, when the forests catch fires, okay? So there is one tree, I don't know, lightning, one tree catches fire, and then what's the behavior of that system? It just gives you to the next trees. And the next trees gives you to the next one. And of course, eventually, if you don't do anything, it just kind of stabilizes and being this thing, I don't know. But this is the behavior of the forest catching fire. Or traffic jam, it's the same behavior. If the cars are here and these are the roads, it's gonna the cars are gonna go this way. And yeah, the book is like 200 pages, and philosophically, it tells you about like stock markets behaves like this kind of one is going to give you the next one is going to be unstable and keep going. Okay, so it's nice to have a quick look at this one also. Now, let me give you one more, and then you slowly see how I'm getting to the directed graphs and monoids. Okay, so one more. By the way, the word in this paper for these systems are called self-organized criticality. So self-organized means that if you have the system, it just starts firing with no input from outside. You saw that, like 10 chips there, it starts firing, and I'm just doing nothing. It just keeps doing itself, like dominoes, right? It just keeps doing. Criticality, and again, this is based on experience, they don't prove it, is that when it stabilizes, as you saw here, it stabilizes, it becomes 2 and it's stable, the whole thing stabilizes, but it's barely stable. If I just push this a little and I put it 3, then it becomes unstable, it fires. And on YouTube, you see, it's exactly like dominoes. I just add 1, and then the whole picture would change, because this fires and gives you to this one, this gives you one, changes the whole thing. So the system is stable, but it's barely stable. That's called criticality. Okay, now let's move on to another paper, comes 10 years later by a physicist called Cstar. And then he is kind of a celebrated theoretical physicist in India. So the system, I'm going to change this a little bit. And you see now, here, it's kind of like a graph, but there is no direction, right? So I'm going to give you direction so that you know if a grain is moving, you know which direction moving. Here, if I give you the grain, it goes up, it goes down, and so on. But if I give you a direction, that means this grain only goes up. if there is a grain here, it doesn't go down because there is a direction. So I'm going to incorporate that into the system. Okay. And I give you just an example. So again, I have a grid, but the grid has directions. Can you see that or make it bigger? Okay. So now, Willie, can you see? Okay. Okay. So it's just called U, V. These are the name of the nodes, S. And the directions is there. Okay, same story. I put grains of sand on this one. But as you see now, if there is a grain here and it fires, on this edge, it's going to go only in this direction. So you cannot go backward. The other thing I'm putting in this system is that, you have a node here. Let me call it S. It's a sink. Call it sink. I'm sure you have seen it last week. Namely, there is nothing going out, right? And everything is connected to this thing in this system, right? Everything, U, V, all you can eventually reach to S. Now, the next assumption I put here is that if the grains of sand or your chips get here, it disappears. So if you are playing poker or, I don't know, some sort of a game, so if your chips arrive here, you are going to lose it, okay? It's a natural thing. It just disappears. Or it falls off the board. So anyhow, so let's do one more. So imagine I start with 4 grains or 5 grains here. So 5, now I'm writing mathematically, 5U. And let's fire things. So see what happens, there are 2 edges getting out. So I just keep this 3 plus 2, 3 grains of sand, another 2. One of these comes here, and one of them go back. Well, sits again here. So 5U becomes 4U plus 1V. Can you see that again? So you had 5. 1 is coming here. That's 1V. 1 moves what gets back to itself, and 3 is sitting there. So I get 4U plus 1V. Okay. Now, the one here, I cannot do anything because it's stable. Because look, here, there are 3 edges getting out. So you can fire this if there are at least 3 grains here. So at the moment, it's just 1. So nothing happens. But this 4, I can write again. 4 of them, 1 comes here, 1 goes back. So I get 3U plus 2V, same story. 2U plus 3V. So at the moment, I have 2U and 3V. Now, this is the part that the abelianness comes in. Namely, look, either now I can fire this because there are 2 grains and there are 2 edges, or I can fire this. Which one you want doesn't matter because it gives you the same result. So let me try this one, okay? If you're trying this, we have to get the same result. Otherwise, the theorem is wrong. So let me try this. See what happens. You have 3 objects here. 2 of them comes here, you lose them. 1 goes back, so you get 3U. So do the game again. That gives you 2U plus 1V. These 2 fires again, you get U plus 2V. So this is what you get out of 5U. And as you see, it's involved. I have to go back and forth. It's not immediate. But this is unique form. Okay. Now, the question is, if I give you a system, at the moment it stays at the level of a game, right? I just, by hand, you just move. If I give you this system and I say, well, when this stabilizes, what kind of properties do I have? Can you give me a mathematical model that I look at that and say, because, let's talk about monoid. Can you give me a sand pile monoid? And in this is E. And you say, oh, in this sand pile monoid, say x plus x is x. Therefore, here you have some behavior. Or in this sample monoid, x plus y, if it's a 0, namely if you give me a bunch of sands, another sands, you do the things, everything gets out, then, in fact, that would not happen, like the sample is conical, then what kind of behavior you have? So you look at this and give me information about this game. And this is what Dar did. So he came up with this monoid, and he could establish relationship between this game, in a way, and this monoid. And as soon as you have a monoid, of course, I'm sure Leo mentioned that you have a group. So he talked about the sample monoid and sample group and how it's related to this one. Okay. I'm gonna, in fact, I haven't yet defined this. So I'm gonna leave it here, move on with the abstract definition of monoid. Then I come back and relate this to this monoid and to the game of those animals I mentioned. So they are all gonna come back together eventually. But before that, I have to tell you about the actual definition of monoid, which is the simplest algebraic object in a way, because you can just add things. Okay, so let me start from there. So I'm going to talk about monoid. This might bore you, but I need to establish monoids. So you start with a set, and I want this set not to be empty. And then the only thing you can do is add. Two elements, you just add them. So you have addition. And you assign to m and n one more element. I call it m plus n. And I want to be comfortable with this. So first of all, the assumptions I put is that you have an element that does nothing. And it doesn't matter in which way you read this. I mean, if you're reading Hebrew, you're reading from right, or if you're Latin, you're reading from left. I want the same, no problem there. So it would be associative. And I really want this to be also abelian. So the order does not matter. So this is an extra abelian. So this is extra I put there. So these are the assumptions of the monoid. But if I put it here, then it's called abelian monoids. But then people corrected me and they said, call it commutative monoid, because somehow it reflects, it's get close to structure of rings. And in rings, when A times B is the same as B times A, we call it commutative. So let's call this a commutative monoid. Let me give you two references. One is this book, Rosales. Garcia Sanchez. I think they are from Spain. It's called Finitely Generated Commutative Monoid. Monoids. And the other one, now this is very much close to the stuff we do. So it's by Fred Verung. And it's called refinement monoids. That means you have a commutative monoid with one extra condition, that when you're working with graph algebras, you always have that extra conditions here. That's called refinement monoid. So he would concentrate on these monoids. Okay. Now, right away, let me give you examples. There are many examples you can come up with. But let's start with the structure of a ring. So you have a ring R. let me just put identity here. I don't know. You have to think if there is no identity, what happens? Okay. So just look at all, oops, R with product. Then you have 0 in there. That's fine. So in a ring R, you can multiply elements, right? You can multiply elements. That gives you a monoid. And I put here, look, commutative ring. Then the elements you multiply is still there. 0 is there also. That's fine. And that gives you a monoid. But the other one is, and if you really want this to be nice, you put an integral domain. Then the element you drop 0. Then 0 is not there. That's fine. Now you have a monoid. In fact, this kind of monoid, there is a topic for that, to study exclusively this kind of monoids. The other one is you start with the ring R, and you can look at all the ideals. All the ideals of R, maybe two-sided ideals. Okay, so collect all the two-sided ideals. This is a monoid because if I get one ideal, I have a notion of adding ideals. So that gives you sum, and 0 ideal behaves like the identity. So this is also a commutative monoid. From any ring, you get a commutative monoid. And the one also I'm sure Leo mentioned is that you start with a ring R, and you get all the class of finitely generated projective module. That's another monoid. Now, don't ask me if they are related or not. I'm sure, maybe you can relate them in some cases, but in general, I don't know. But from one ring R, I could get 3 very, very different kind of monoids, all coming from the structure of a ring. But of course, N or 2 copies of N, these are also all monoids. Okay. So very quickly, if you have 2 monoids, M and N, so you have a map which respects the addition. This you call morphisms of the monoids or homomorphisms. And here I really want 0 to go to 0. So I have to put this extra condition, okay? 0 goes to 0. And the other thing is I have a notion of a free monoid. So let me just talk about the free monoids. And that gives you a lot of examples immediately. As soon as you have a bunch of objects, you can get a free monoid out of that. So what does that mean? So you start with a set S a set. This can be also empty, but if it's empty, then the free monoid associated to this from the definition becomes 0 monoid. But let's not concentrate there. So S is a set. Then I say F is a free monoid. Now this F is a free monoid. You need to have this phi there. So you have this gadget. So F is a monoid with this map. It's free. So F is a free monoid with generators S. If you give me another one and another map, there is a unique map, now homomorphism, going from F to M. Okay? So in a way, any morphism goes through phi. But this phi, the way I understand, this has to be there. Okay? So if you give me another map, it might not work with this map, this property that I said. So this phi comes with the definition, although when I say free monoid with generators S, I don't say that phi, but this phi is implicit there. Okay. So, and the game you play is that, okay, you have this S, then that F becomes just S copies of N. This is your F. And it has that property. All right. So now immediately you can see that if you give me S, And if you give me a monoid, any monoid, and if you give me a map, just a map, so throw elements of S into M, you have an equality between these, and then this free monoid here, and M. Yeah. This is free commutative, of course. Yeah, this is free commutative. You're right. That's why I said N. You're right. There is a free non-commutative one. Then you have to just you have words and put the words next to each other. But this is, again, to me, this is, look, this tells me that if you are just working with no algebra, there is no algebraic structure here on S. You just have S and a map. But then here it turns out you're working in algebra. You have a homomorphism between these. So this is the first step that somehow you don't need to work in algebra. You just need to work in this between maps here. If you're working with free monoids, just sort of. Okay. Now the next step, because eventually I want to define this graph monoids. So let me just do sort of more abstract setting of quotients of monoids. I'm sorry if you know some of these, boring, but let me just establish them. Okay. So quotients of the monoid. Okay. So if you have a monoid M, and you know, through this, I'm just talking about commutative monoid. And if you have an equivalence relation, that means that you can always compare A and A, and if you're comparing A with B, then you can compare B and A. And if you connect A to B and B to C, then you have A to C. This means equivalence relation. And this equivalence relation respect the structure. So this one respect the structure, meaning that if A is related to B, then A plus C is related to B plus C for any C coming from the monoid. Okay, so the relation respects the addition. If you have that, then you can define a new monoid, so to say the quotient monoid here. So you get the equivalence classes. So let me call this the equivalence classes of A. These are all the elements in M such that they are related. So now you're collapsing all the elements which are related to A, and you show it as A. And then you can define, let me call this M. So these are all these elements. So you see, for different A's, you might get the same thing here. But the way you define it is that A plus B, I mean, the most natural thing really, A plus B. So now this gives you a monoid. And let's call it the quotient monoid. Yeah, I mean, you lose, of course, some information because you're identifying a lot of objects with the same one. But this is the quotient monoid. And as one concrete example, if you start with a submonoid, so submonoid meaning that this I itself is a monoid and it contains the zero of M. Okay, so it could be zero also. So I is a submonoid. Then I'm going to define an equivalence relation. So this is just submonoid, right? So submonoid. I would say A is related to B if, so A and B are coming from BM. If A and B are related, if you shift, I don't know if this is the right way to say, shift A with some elements of I, it would be equal to B if you shift it with some, possibly another element. If that happens, for some, then I say A is related to B. Okay, you can prove that this is an equivalence relation with all these properties. So A respecting addition. Then let's call M with this, maybe this one is the quotient. Again, I'm not sure this is a good notation here, but let's use this. If you are working with groups, and we are always very comfortable with groups, right, with abelian groups, this means the usual thing we are comfortable. That means A minus B is inside I. Remember that when you're working with subgroups, this becomes an equivalence relation, and then you had this sort of a group over I, the real quotients that we had. But you don't have sort of subtraction in a monoid, so that's how I should do that. And I wrote this, but then you have to be careful when you're working in the setting of groups that we are very comfortable, then 0, the equivalence of 0 is exactly I in groups, right? So this I, everything claps to 0 in the quotient. But this is not the case in the monoid. These are not the same. So you see, a bit of complications comes in. So you have to be careful here. Okay. So what's the time? How long can I go? 5 minutes. Okay. So I'm going to give you 2 more concepts in monoids, and I stop there. I would tell you what it means by ideals. So you have M, a monoid, commutative monoid. What does it mean to say ideals? And what does it mean to say a face of a monoid? And pretty much that. And you see, these are a bit different than the one we are used to in group theory and in ring theory. So what is an ideal? So I is a subset of M. And let's call this I. Let's imagine I is non-empty. In some literature, actually, they say maybe it's empty. But let's call it non-empty. Then I say I is an ideal if this happens, that I plus M absorbs the whole M. It's very similar to ring theory. You know, you multiply from left and right, and you stay in the structure. It's the same here. So can you tell me, so yeah, so this is an ideal, definition of ideal. I plus, you add it with any element of M, you're still in M. So component-wise, this means that, or element-wise, this means that I plus M is always in I for any I in I, and for any M in M. So this is the same way to say that. Could you tell me what would be I if it has a 0 element? If 0 is in I, and I is an ideal, what do I get? So if 0 is in I, then what do I get? M, everything, that's right. I is the same as M, because I just pick 0, and then all the elements are ideal, then I is the whole thing, so similar to that. Okay, so this is an ideal. What is a prime ideal? I is prime ideal if, first of all, I is not M. Maybe I say if I is an ideal, I is not M, and if the sum is in I, then one of them should be in I. This is a prime ideal in monoid. But let me give you an example. I came up with this example last night. So if your monoid is 1, 2, and with multiplication, right? That makes sense, right? With multiplication, this is a monoid, and I is 1 is the identity. Then 2n, the even numbers, well, this is an ideal, and it's a prime ideal. This is the ideal of the monoid n with multiplication, right? With multiplication, right? Yeah. And because 2 is prime, then I can prove that if two things is in even, then one of them has to be even. Yeah. And this is the one, and then almost the last notation that I'm gonna put in here. And this is the one that I said has different names depending if you are coming from topology or geometry and so on. So in the theory, in this theory of Leavitt path algebras, they call it ordered ideals, and then there is a problem because it's not an ideal, but they call it ordered ideals. But in other places, they call it face of the monoid or a saturated, I think, saturated ideal or something. So depending on where you come from. Okay, so what is that? This time, I is a subset of M, is not empty. Let me call it face now. I know this is not in line with Leavitt path algebra terminologies. It's called face because it's not an ideal. If I is a submonoid meaning that you have two elements, you can add them, you stay there, but it doesn't mean that that element plus any element of M you stay there. Submonoid, and if x plus y is in I, then x and y is in I. So have a look at this. I know these are kind of similar. Oops, yeah, I should have said prime ideal is x plus y is in I. Then I should have said like prime ideals x or y in I. So like prime ideals. So order ideals, I keep saying order because I work with this Leavitt path algebra or face. If the sum is in the I, then both of them has to be in I. For example, this is not of that nature because if 2 times 3 is in here, but 3 is not in here, so it's not an order ideal, or it's a face. Okay. Maybe I just tell you this as an exercise and leave it there for you, and stop there. And then more interesting stuff starts from tomorrow. So I had to get these out of the way, and then from tomorrow I talk about graph algebras. But have a look at this because I have a bit of an issue here. So I'm going to talk about localization. And these are all, parallels to ring theory. So very quickly, so imagine S is a subset. So when I was looking at this, the text that I was looking, it said S is a subset, but I think it should be more than a subset. So I put that as an exercise. I think at least it has to be a submonoid, but maybe it has even to be ordered ideals. You'll see in a second, it's not very difficult to figure it out. Okay, so I say here, S, I think, has to be at least submonoid. Okay. Then the localization, and this might remind you as of ring theory, is the quotient of S times M with an equivalence relation. And here, I'm just going to write it this way. Sm is related to S prime, M prime, if M plus, or maybe M1 and M2, oh, it's okay. M plus S prime plus some T is the same as M prime plus S from T prime. And this T and T prime also coming from S. Okay, so you can check that with this equivalence relation, you get the equivalence classes, and that makes it a monoid. So I have to give you how they are added. So if you have an element here, and you add with the next one, you just add this way. So that's why you need this to be closed to start with. Okay. Or some other places, you can write this SM or SM or MS as M minus S. And that tells you that I'm basically creating invertible elements for S. So anywhere in your monoid you have S, in this new monoid you have inverses for S. So this is called the localization. And as soon as I get S to be the whole M, so if S is the whole M, then you are working with S times M. And this would be what Leo called the group completion of M. So you have seen this one before. The group completion is basically M times M with this relation. All I did instead of M, I put some submonoid, and it worked out fine. And I think as an example, so if you are, so I'm going quickly here, but I'll leave it to you to figure it out. So if you are here, then the group, this is M. And the group completion, we work with this. We are going to work with this, is Z times Z. So the group completion of N is Z. The group completion of this product is Z times Z. But with localization, you're allowed to construct this situation. So you flip one component to a group, and the other, you keep it there. So if you allow yourself to not get the whole thing, but just bits and pieces of the monoid, then you're allowed to go from here to here, and then maybe you go one more steps and you get the whole group completion. All right, thank you. I'll stop here, and then tomorrow I start with graph monoids. Thank you.